So does it look like a star blew up and kind of left its remnants? That's kind of what that is. Okay. The video we watched talked about a lot of times stars can be born when we talk about open clusters and globule clusters, they're born in the same kind of fodder. So they're called giant molecular clouds, and that's a term we'll run into in the next unit, the next chapter. But in order to understand how stars live their lives, we can see all sorts of stars at different stages of their lives. Okay. So the term nebula, we've kind of run into a few times. And again, nebula is basically a region of kind of dust stuff, okay, that may or may not kind of birth stars. So when we talked about our sun turning on, we said that the solar nebula had to, in the core, which was the center of the solar nebula, was going to become our sun, it needed to get hot enough and dense enough to begin nuclear fusion, and that's the same deal with these stars. Okay, so gravity needs to kick in and make the conditions in what's going to be the core of the star hot enough and dense enough. So in terms of kind of the blob that ultimately births stars, okay, it takes a lot of mass to create just one star. I think that's the point there. So this could be kind of something that's going to birth a cluster of stars. And the word fragmentation, you're going to kind of see it play out on the next few figures. It kind of gets like little nits in there that can become stars in and of themselves. Okay, so that's, the first one is kind of what we call homogeneous, and this is where it kind of starts kind of blobbing together. Okay, oftentimes something maybe disturbed the cloud that's going to birth stars. So these lumpiness can begin to begin kind of the contraction process that can ultimately create the conditions needed for a star to be formed. So the more lumps you have, the more stars you be born. You know, a lot of pictures you look at in astronomy kind of have this red sort of look. You know, and honestly, probably they're just looking at it in infrared or something like that. So, making a cluster of stars. Okay. So this actually, from what I can tell, is actually a photograph then of a cloud that is birthing stars. And this looks very foreign, but if you look again, it has the word Orion in it. So honestly, though we can't see it with our eyes, if you were to switch to look at different wavelengths, this is what the region of Orion's sword would look like, the constellation Orion that has the three belt stars and the sword hanging down from it. Okay, so this is looking in the infrared region. So this very much reminds me of the chapter on the formation. Actually, it was the previous unit, not just this unit that included a chapter on the sun. But when we said the formation of the sun from the solar nebula, this is kind of what we talked about, very similar. Doesn't that remind you of our solar nebula? Okay, our solar nebula started out as kind of a blob that had a little bit of spin to it. As the blob contracted, it heated up, converting potential gravitational energy into thermal energy. And the spin, as it contracted, just like a skater brings in her arms, it went faster. So this kind of makes sense that a lot of stars out there that have formed like this disk region can form planets, right? So you're like, hey, what the heck? Okay, this is very similar to what our sun went through. Looks like our sun. On the chapter when we talked about our solar system and including the sun and the planets. It's like deja vu. Okay. Well, one of the things that we can see, bless you, in other stars are these jets, okay? Kind of jets of energy that come out of the star, kind of what, perpendicular to the plane of you might have the planets forming, okay? So these could form planets here, and this is jets of energy. Not necessarily as the star began thermonuclear fusion in its core. One of the things is, you know, it didn't turn on because it doesn't look like it's kind of cleared. It's just like our sun had solar wind to clear its area of dust and stuff. That dust is still there. This is a protostar. You kind of heard him talk about a protostar. So the term protostar, no nuclear fusion yet in its core. It's nice and toasty. It's got the spin going, okay, but it's still not fusing hydrogen to form helium. This is birthing of stars caught in action. Okay, so protostar is a pre-star. And then if anybody asks you on a test or otherwise what classifies a star as a main sequence, I hope you kind of, let's see, how do I want to, the words hydrogen fusion would probably do it. Okay, so our sun is a main sequence star. Most stars are main sequence stars. You see them on an HR diagram, kind of that diagonal. And all of what they have in common is in their core. They are fusing hydrogen to form helium. So now actually we're going to talk about, as stars leave the main sequence, they do something else in their core, and we're going to talk about that. So to kind of summarize the process, okay, before kind of from a blob to a protostar to a main sequence star, gravity basically makes the thing squish down. Okay, we talked about fragmentation as a way to maybe within the same giant molecular cloud to get several stars to be born this way. And then that little blob that's going to become a star, maybe planets, okay, goes ahead and gets smaller and smaller. It warms up as it gets smaller. If it's got rotation, it can have planets. That's funny because when stars are born, if they have rotation, then they get this disk that they can, no rotation, no planets. It's, number 4 is kind of almost poetic. The new star achieves long-lasting state of balance. Okay. Okay, so that state of balance is a main sequence. For instance, that nice state of balance for us is, what, 10 billion years. So open clusters of stars that are really near each other, okay, were oftentimes born at the same time. Globular clusters born at the same time. All right. So this is one of the things I thought I heard on the video, the part of the video that we watched. Remember they talked about the red dwarfs? Did I talk about red dwarfs? Red dwarfs, by the way, are just main sequence stars. I'll show you the red dwarfs. Okay, they are adorable. Okay, so these are red dwarfs. Not to be confused with white dwarfs, or we're going to talk about brown dwarfs too. Like, really? So red dwarfs are nothing other than a main sequence star that's down here. They are red because they are cool, and they are small. They're just low mass, but they can't be less massive than 0.08 solar masses, right? So these are very common, but we don't see them because they're so dim. The ones that catch our eye are the big ones, and those are kind of rare in general. So we already kind of talked about this a little bit, the two ends of extremes on the star's mass. This actually was in the last chapter. So why is 100 solar masses the upper limit? Well, this kind of describes why. If you get more than 100 solar masses, basically when it begins nuclear fusion in its core, it's just unstable, and it blows off some of its stuff. It just can't keep its stuff. Okay, so I said 100 solar masses is the upper limit for the mass of a star. Notice, though, that there are some, I would say this is an anomaly. You know, you can get massive stars out there. So this might make sense to you too. You know, we talked about, you know, the thing that during fragmentation, the amount of stuff that's set aside, that it's ultimately gravity's going to kick in and make it in its core the sufficient temperature and pressure to begin that fusing hydrogen atoms. Well, during fragmentation, if it didn't have enough mass to ultimately let gravity kick in and let it have nuclear fusion in its core because of its temperature and pressure, then it's a failed star. And 0.08 solar masses tends to be that mass it needs to have. Okay, so it will get warm, okay, but it will never get warm enough in its core. So one of the scientists talked about degeneracy, and actually in the video we watched, he talked about electron degeneracy. Okay, basically electrons don't want to be next to other electrons, so they stop the whole kind of collapsing thing. Okay. I'd actually say with most matter, the reason, you know, two objects don't want to occupy the same space. You know, I have two black objects up here. The reason they don't go through each other is because atoms in this one and atoms in this one have electrons around them, and they're not gonna, they won't flow through each other. Okay, so electron degeneracy is something we're kind of familiar with in every day. Okay, so, do you remember when we talked about, the sun? And I'll kind of draw a little diagram here, I think. Its gravitational equilibrium is what I'm after. In an earlier chapter, we said if this is kind of the orb of the sun, we said that gravity would go like this, okay? Okay, but since our sun is active, we said that it actually, from the energy in its core, is going like this, okay? So that actually kind of is a good way to kind of think of this degeneracy of thermal energy or heat. This down here is a way to kind of think of electrons or particles. It could be electrons, it could be neutrons, okay, that will not occupy the same space. So it's like they're playing a game of musical chairs, okay? So here there's plenty of room for them all to kind of, there's extra space, okay? They don't have to be squished together. Here, if you count the people, let's see, everybody's still got a chair, but they're squished together. They cannot sit on top of each other. Okay, so degeneracy, the thou shalt not sit on each other still works, the second one down here. Okay. So I mentioned there's a red dwarf, there's white dwarfs. First we talked about white dwarfs, retired stars, and then we talked about red dwarfs, which is kind of the low-end mass of the main sequence stars. And now we have brown dwarfs. Okay. So what brown dwarfs, I've called them failed stars, and actually they made it to, in this chapter, as a review item for your exam. So brown dwarfs are failed stars, and they're less than 0.08 solar masses. So basically a part of a fragmentation said, I want to make a star, and there wasn't enough mass. Okay? Because what you see here basically was the matter itself said, I'm not collapsing any further. Okay? So brown dwarfs. So some of you I know or are curious, and we'll talk more about this, but are curious about dark matter. Okay? And you're like, brown dwarfs, dark matter. Well, all dark matter is we know that there's mass there, we just can't see it. So honestly, if there's something that's not lighting up, like a brown dwarf, that could actually kind of help account for some of the mass that we call dark matter. Not all of it, but some of it. So brown dwarfs. There's kind of a fine line, and I've heard somebody kind of describe this to me. What's the difference between a large planet? No, this isn't a joke. It doesn't sound like a joke. What's the difference between a large planet and a failed star? You know, there are some similarities there. So, talk about kind of failed stars. There are these stars that will never go ahead and go create nuclear fusion in their cores, kind of indicated by the circles there. It makes sense if you have a stellar nursery, some of them, the fragmentations are not going to have enough mass. Okay, so stars more massive than, I say, 100 solar masses. So if on my test I ask you, what's the upper mass limit of a star, I think you should say 100 solar masses. And on my review sheets, instead of putting 100 solar masses, instead of putting the sun here, I went ahead and it was easier. I just put a circle with a dot. It's the same thing. So to summarize, in case you're asked on the test, wink, wink. Because honestly, I think this is one of your terms. It's a phrase more than a term. So these end up as brown dwarfs, okay, if there's less than 0.08 solar masses. And then if they're larger than 300 solar masses or than 100 solar masses, I guess I should say, sometimes they kind of settle in, they lose some weight, and they make it so they can be just a regular star. All right. So I need to kind of throw another sort of generality at you. I use the 0.08 solar masses as a failed star, less than, if it's less massive than that. I'm introducing another term, a low mass star. And a low mass star, actually, our sun fits in a low mass star. Because look what a low mass star is. Put another way, a low mass star needs to be greater than 4 solar masses. So let's see, I'm not good with my greater than, less than sometimes. Okay, low mass star needs to be greater than 0.08 solar masses. Okay, but it needs to be less than, I think that's right, 8 times the mass of our sun. Does that make sense? So the reason I need to talk about low mass stars is they have a different life than high mass stars. Just to kind of let you know what this is looking like or where we're going with this. In a minute, I'm going to talk about high mass stars. Oops, high mass stars. And guess what? They are simply going to be more heavy or more massive than 8 times the mass of our sun. All right. So if you were going to put something under your pillow, you'd want to make sure you could read it. But this actually, kind of in a nutshell, is what low mass stars do. And actually, they, on the video we watched, talked about these different stages. You see this? These are the jets from a protostar. Okay. This actually, it's hard to see it, but number 2, I can read the words yellow main sequence. So right here, this is a main sequence. I'll put MS. This actually is a protostar. Okay. Then these over here are things we still need to talk about, but he talked about them on the movie. So if you're kind of a visual sort of person, you can see kind of the giant, the red giant stage. And we're going to see it kind of goes back and forth a little bit. It settles back into something else. And then it goes back to a red giant. And does this look like a nebula? Kind of like he talked about? This is where it's creating a nebula here. A planet, we call it a planetary nebula. It has nothing to do with planets. But when a star is kind of near, just ready to become a white dwarf. Okay? So nebula. I'll actually go ahead and call it a planetary nebula. And over here, white dwarf. Okay, that's white dwarf. And these are giants. Notice what's missing here. It doesn't blow up. So at the end of the video, he kind of talked about a massive star will, no. And if it's less than 8 solar masses, it does this. Sort of. So this is just to kind of remind you that by definition, and you do have some definitions on your test, by definition, a main sequence star, like I said, must be fusing hydrogen in its core. And one of the things we talked about with our sun, fusing hydrogen into its core, remember we had like the 4 hydrogens goes to make 2 heliums and blah, blah, blah. Main sequence, by definition. So, you can see the HR diagram. Remember, that's one of the things you're going to want to kind of wrestle with. Remember, on an HR diagram, we have surface temperature, but it's the hottest over here and the coolest over here. It's kind of backwards. Okay, and then on the y-axis, we have luminosity. Okay, so kind of dotted in there is the main sequence. So the cool thing about this is, that's not cool. The cool thing about this is you can kind of see the main sequence line. So up here, we've been talking about those are giants. And so here you see, and that's another thing I'm hoping that you've gathered between that, the previous chapter and this chapter, is that when we say a star is moving on the HR diagram, basically the first big move is it, after it's done humming as a main sequence star, it leaves and it goes up to become a giant. That's what we say moving.
Does it come back, like after it's a red giant, and it comes back, like after what a blue stars are those the ones that come out of the red giant section?
No. No, the blue ones up there are just, they're still humming as main sequence stars. It's just when they started, they had all this mass. So they're just regular main sequence stars. They are just more massive than these guys. So, but we are going to see that there is a little bit, and it's coming up here in a minute, but there's a little bit of a kind of a wiggle. And they call it the horizontal branch. It kind of wiggles a little bit as it's left the main sequence.
But the bigger ones, or the more massive stars, will blow
Right.
up. They won't go down to white dwarf, but will they go up to the giants?
Yes, they will go up to the giants before they blow up. That, it just sounds so funny. Start blowing up, yeah. Really? Blow up?
No, giants.
Oh, okay. Are they still in it? No. Okay, well, if you don't know, I don't know. They're not? Okay. So when we talked about the sun, we talked about this kind of subtle little thermostat, kind of like you have a thermostat in your house. If it gets a little bit cold, it'll kick on until it gets nice and toasty, and it'll kick off. Okay, that's a thermostat. Well, basically what happens when we run out of hydrogen in the core to fuse, okay, is that outer pressure slows down. Okay, and when the outer pressure slows down, okay, that when I say outer, I mean the energy from fusion going out from the core, it slows down. So what happens is the star starts to kind of collapse on itself. And on the video we watched, it talked about a climber trying to climb and escape, and that was all well and good when there was enough energy kind of pushing him. Run out of hydrogen to fuse, and gravity kicks in, and the climber falls back down to the core. That's kind of what's going on here. So as that happens, what can happen is we get a squished region right outside the dormant core. I know it's kind of confusing. I don't think it made it my test this semester. But when the star basically starts to kind of collapse on itself, why? Because it basically converted all of its hydrogen to helium in the center. That's the pink. Helium's the pink. It creates a new region outside the dormant helium. Now that right out there, we call it the shell region. Now it's, because it's squished, it's got enough temperature and pressure to go ahead and begin fusing hydrogen. Okay, it's got the fresh hydrogen. It was never part of the core in the first place. So now we have shell hydrogen fusion. And our sun is going to do that. Okay. Ultimately, what's going to happen with our sun is this. So if you look at this, this is a different type of fusion. And what fusion is basically taking nuclei, like you see these kind of, remember we have protons and neutrons, okay, representing these three different nuclei of three helium atoms, squished together, and you can make one center of a new atom. It's a heavier atom. It's carbon. Different properties. Don't you think carbon and helium are kind of different? Just whatever comes to mind. Carbon is something you can sink your teeth into. Helium is a gas. Okay, so we get something new here. And that actually eventually is going to happen in the core of our star. But it's not going to happen until the temperature ramps up in the core. Because to take helium and make carbon out of it, and I think the next chapter, I have like a little slide to say what temperature that needs. But it's a bigger temperature, a higher temperature than the whole hydrogen fusion thing. And this talks about if the certain mass stars go through this kind of abrupt beginning of burning helium in their core to create carbon. So the pink generally is showing you helium. And here it's showing you, it says helium core fusion. So helium core fusion. Helium must be forming carbon then. And we have our hydrogen shell fusing around it. But I told you kind of if this is main sequence, okay, and so up here, kind of the upper and kind of the right, those are your giants. Okay, so they are swelled. And can you kind of see the swelling here? We said that when the sun, when our star runs out of hydrogen to fuse, it'll all be helium, it's going to swell. You see the swelling here. Notice that our sun should reestablish more nuclear fusion in its core, but it's not going to be hydrogen fusion, it's going to be helium fusion. One of the things about these later fusions, these heavier element fusions, is they don't last very long at all. Okay, so it's not 10 billion years at all. Now mine will be a crispy critter, okay, but so when somebody talks about using an HR diagram to kind of track the life of a star, this is what they're talking about. So the star will move on the HR diagram. I like this one because it takes you a minute, took me a minute anyway to kind of, but of course it starts here and then it goes here. Don't worry about the subgiant versus the red giant, okay? But you see it go back down here again, then it goes up here again, okay, and then it goes over here. Oh, and this is kind of maybe what Aaron was saying. It looks like it's kind of going like through that. And it won't take very long though, and it ends up here as a white dwarf for a while. And then the guy said, did you hear him say that it's like somebody retired, he's basically gonna glow until he will be just a, nothing. I called it a brick down here, okay, because it's eventually gonna ooze away radiate away its energy.
So it changes from this position up to that position for a while before it goes on back down all the way to the white dwarf.
Mm-hmm. Yep. And these, it's a little deceiving, but just to try to kind of reiterate, this main sequence takes a long time. All this main sequence. And then the other kind of wiggling around, not so much.
So that would be the track of the sun.
Mm-hmm. Yep. Okay. So kind of that wiggle that you kind of saw going back and forth in the giant region. Okay. That's called the horizontal branch, kind of a little bit of wiggle there. Before it kind of ejects its planetary nebula and comes back down to white dwarf stage. So, this actually is an identical slide to what we covered just a little bit ago. Okay, and again, it's talking about taking a group of stars that are all born about the same time, and you told me that these guys up here, if these are all main sequence stars born about the same time, these guys are going to leave first, right? Because they're most massive. And then the thing is, and we looked at a few of them at the end of the last chapter, you look for the turnoff point, okay? So like if all these are gone, okay, this would be the turnoff point, for example. And finish that thought, the lower the turnoff point, the older the cluster. Does that make sense? Okay. Oops. Really? That's all it has? Okay. Well, so shell fusion, I told you what shell fusion was. Shell fusion is basically kind of an interesting sort of thing. The shell in shell fusion means it's kind of outside of the real core. Okay, so basically you have fresh hydrogen that once the star gravity was kicking in and kind of compacting it around the spent hydrogen, which is helium, you have fresh hydrogen that can go ahead and begin fusion. Okay. Now, the guy in the video you saw talked about an onion. Okay, I'm kind of setting you up for an onion. Okay, and what an onion is, ogres are like onions, right? What an onion is basically kind of, shell after shell after shell going out. So, kind of similar to hydrogen shell fusion, we kind of have we can have a series of shells, and the heaviest fusion in the core and going out the lightest fusion. So isn't that pretty? So we've seen some just figures tonight, but that is a photograph. And that's sometimes called the God's Eye Nebula. So you saw in the HR diagram what a nebula is, right? It's kind of it's right before retired star, right? White dwarf. So somewhere in there, in the center of a planetary nebula, would be the white dwarf. I'll just put WD for white dwarf. And these will glow for a while, but eventually the nebula will stop glowing too. So remember, if somebody says, oh, that's a nebula, that's a planetary nebula, it has nothing to do with planets. Okay, it simply means that it's kind of talking about a star that is ending its life on its way to retirement, and it's a gravity thing, kind of the blanket that it's kind of made, and I use the word cocoon on my review sheet. It's kind of like a cocoon of material that was the star. It just kind of lifts off and makes these cool shapes. Okay, so planetary nebula is just part of the life cycle, kind of. Okay. So remember what we said low mass was. I hope we're all kind of on the same page here. Low mass is less than 8 times the mass of our sun. I'm going to kind of clean things up just a little bit. I'm going to talk about a low mass star that has kind of a different sort of end to it than a white dwarf. But when it's talking about degeneracy pressure, you know, I think, and I think the video did this, I think you can call it just simply just normal degeneracy pressure. And the reason atoms don't, like I said, atoms don't share the same place as other atoms is because the electrons. So I think that's a type of electron degeneracy pressure. Just typical, I'm done collapsing sort of thing. I can't animate this one, but I'm kind of leaning towards let's go ahead and take a break, and I will pull this up so we can see this animation. There was another little movie before that too. So 10 minutes, and I think we're doing pretty good for knocking out this chapter.